So in this video, I'm going to talk about other additional integration techniques. So the first one is integration by parts. So here is the formula. If a function, you can view it as u integration u dv. This is going to equals to uv minus integrate v du, or by a defined integral from a to b u at dv. This is equals to uv from a to b subtract from a to b v at du. I'm going to explain how to use it. Okay, now here is the first example. I have x e to the x at dx. So in order to use the by part formula, now I need to break the product into two parts, because as you can see in here, I have a u and dv. So if I let u is equals to x, so if this part is our u, so that means the rest of it is going to be our dv. Okay, so if we decided to let u is equals to x, so that means our dv equals to e to the x dx. Okay, so now look at the first part. So u is equals to x. So now let's get derivative on both sides. So du dx, which is x derivative. So I have a du dx. Du over dx is equal to 1. The derivative of x is equal to 1. And then, so that our du is equals to 1, I'm going to times dx on both sides. So I can cross cancel the dx. So that means du is equal to dx. Okay, so now the next part is v. dv is equal to u to the x dx. So now I'm going to take integration on both sides. If I do it together, it's not going to change the value of the function. So integration and derivative. Basically, derivative is what antiderivative. If you get the antiderivative and then derivative, that means you will get the original function, right? Nothing is going to change. So that means on the right side of the on the left side of the equation, this is equal to v, and then on the right side of the equation is you're trying to get the integration of e of x. So we got this is e to the x. Right now, you don't need to worry about the plus c part. So now we have everything that we need. So we have our u, we know that dv is equal to e to the x, and because of that I got v is equal to e to the x, and then I differentiate u, I got is equal to dx. So now let's do the substitution. By the formula, I know that, hey, uv subtract integration v at du, that's what the function equals to. U is equals to what? U is equals to x. V is equals to e to the x minus integration v. Our v is equals to what? Ex du at here is dx. Now we just need to integrate the second terms of the equation. So this is equal to x subtract e to the x. So now we're done at c. So that means the integration x times e to the x is equals to s times e to the x minus e to the x plus c. Again, if you're not sure if this is your answer, you can just do the checking, right? Okay, so now let's have more examples, such as I have (1 to the 4 6 x squared ln x). x at dx. Okay, so for this part, since this is contain a logarithm function, so we will use that as our u. So that I have, if I let the logarithm function, this is our u. So u is equals to ln of x. So when we get the derivative at u at x is equals to the derivative of ln x, which is 1 over x. When I simplify it, I have du equals to I times dx on both sides. So, oh, sorry, I should cross the wrong one. So I have 1 over x at dx. Okay, so now we still need to find dv, because the function is equal to u and then times dv. So that means the rest of the part, this whole part is going to be our dv. So our dv is equal to 6 s to the q x squared at dx. Now we integrate the equation on both sides. I have dv integrating x squared at dx, and then these antiderivative and derivative, they cancel. So I have v equals to whatever that integration is. So this one should equals to 6 times 1/3 s to the cubed function. Okay, so when I simplify, I should equals to 2s cubed. Okay, so now we have a u, du, dv, and v. These are the things that we are looking for. Because when we're using the integral by part formula, I know that this is equal to uv from 1 to 4, subtract v du also from 1 to 4. Alright, so now I can just do the substitution. U is equals to ln to the x times our v, which is 2 times x cubed, again from 1 to 4, and then minus from 1 to 4 integration v, our v is 2x cubed, and then our du is 1 over x times dx. Simplify it. So from the first one, I have ln to the 4 times 2 times 4 to the cubed power, subtract ln to the 1 power times 2 to the 1 to the 3rd power. Subtract the integration. So I simplify this, I got 2 times x squared dx. Okay, so ln to the 1, we learned pre-calculus. I know that this is always equals to 0. So that means 0 times everything is equal to 0. So this part is 0. So, and then for this part, I got 128 ln to the 4th. And then subtract whatever integration this is. This one is equal to 2 times 1/3 x to the cube, and then from 1 to 4. Again, when we simplify that, I have 128 times ln to the 4th minus 2/3 times 4 to the cubed power, subtract 2/3 and then subtract 1 to the cube. So there's one thing you need to be careful, is this subtraction is subtracting the whole defined integral. So that means in here, it's better for you to put a parenthesis so you won't forget it later. So because the sign in here is going to change, and then you can use a calculator to help you to find the final answer. So now let's do another example. So if I want you to integrate ln of x at dx. How to integrate this part? Again, we can use our integration by parts. So in this case, I will let u equals to ln of x. So in this case, if this is our u, so that means the remaining part should be our dv. So that means dv is equals to dx. Now, after u, we still need to find du. Well, if we differentiate the equation on both sides, I got du over dx is equals to 1 over x, so that our du is equals to 1 over x times dx. And then our v, if I integrate v dv on both sides, so I end up to be antiderivative and then derivative. So that means they cancel out each other, so v is equals to x. Now I can substitute that into the function. I have uv subtract v at du. So uv is u is equals to ln to the x times our v, which is x, minus vx. U is equals to 1 over x at dx. So simplify it. This part basically is 1 at dx. So this is equals to what? This is equals to x, right? Because we're derivative of x, you got 1. And then don't forget to plus the constant term. Okay, so this is the technique by integral by parts. So another technique that we use is called the table of integral. I'm going to attach that to the lecture notes. So lots of times, even though we use u substitution and the integral by part, there's still lots of complicated and such as logarithm or square root of the polynomial that we cannot be able to integrate. Then in this case, we made a list of table. Basically, it's a formula that you can use that apply for your integration. Such as, I'm going to attach that to our lecture again. Integrating 1 over x squared minus a squared. So this is equals to 1 over 2a ln x minus a over a plus x plus a plus c. So to do this one, let me give an example, such as 5 over x squared minus 9 dx. So this one, okay, doesn't look like I can use any of these formula because I need a s squared and a squared, and I want the numerator equals to 1. Well, the numerator equals to 1 is very easy fix, right? We just need to pull the 5 out. Now I take care of 1. So how can I make these two similar? I have x squared. The s squared part is taken care of. But what about the a squared? Well, I have 9. Well, if you think about it, what square is equals to 9? It's going to be 3. So that means I have a 5 outside, and then x squared minus 3 squared, and derivative. Now I can apply that to the formula. So I have 5 times whatever that is, 1 over 2a. Our a is equal to 3. So that means it's 2 times 3, ln absolute value x minus a, which is 3, over s plus 3, absolute value, and then whatever that is, plus c, a constant. So that's the application of table of integral. Sometimes you will see something that more complicated. You need to do some manipulation. Such as, here is another formula from the table of integral, which is 1 over x squared plus a squared, and then square root the denominator. That dx, this is going to equals to ln x plus square root of x squared plus a square root plus c. Okay, so the example is such as 1 over, no, let's use x squared over x to the 6th power plus 16. Alright, so now what do they have that makes you feel like, okay, I can use this part? Well, first thing is the a squared seems reasonable and they both have square root in the denominator. So maybe if I do some manipulation, I can make that happen. So now I can try to rewrite it as x squared. So 6 to the cubed, okay, that's hard, right? Because I want square, I want 2nd power. Now you give me the 6th power. Well, what if I write it as x to the cube and then square? Because this is equal to the 6th power plus 4 square root at dx. Okay, so now this is getting closer, which means our x is equal to x cubed. And then our a is equals to 4. But however, the numerator is x squared. I still want to get rid of the x squared. Well, maybe time that we use some technique that we learned before, such as the substitution. Okay, so now let u equals to x cubed. So when I would write the function, I will have x squared over u squared plus 4 squared at dx. All right, so now we differentiate du on both sides. So this part is 2x squared. So that means by using u substitution, I have dx is going to equal to du over 2x squared. Well, now I substitute this part back into our dx. Which is du over 2x squared. Well, now the x squared, they get cancelled out. So these two cancel out, and then I can even pull the 1/2 outside. So that means now the function is equals to u squared plus 4 squared at du, which means I can apply this formula now. Our x equals to u, and then a is equals to 4. Don't forget to multiply the 1/2. So this is equals to 1/2 ln x, which is our u, plus u squared plus our a squared, which is 4 squared, and then absolute value, and then as the constant term c. But this is not done. Whenever we see the u, we need to substitute, I need to substitute u equals x cubed back to the function to finalize it. So this part is equals to 1/2 ln absolute value u is equals to x cubed plus square root of x cubed x to the 6th power plus 16 absolute value plus the constant term. Okay, so that's it. So there has a very long list of the table of integration. Please check it out, and you might need to use that for your homework. Okay, let me know if you have other questions for this part. See you next time.